Dave Brown for Teletrain. Today we continue our study of solid-state electronics with Chapter 6, which is entitled Oscillators, Modulators, and Demodulators. First, let's discuss oscillators. Oscillators are very important in electronics. They are in all radio and television transmitters and receivers, in signal generators, test equipment, radar, and industrial electronic equipment. What is an oscillator? An oscillator is simply a circuit that generates an AC signal with only a DC input. This AC signal may be a low-frequency signal, an audio frequency signal, or it can be a very high radio frequency signal. How do oscillators work? If we take a part of the AC output signal from an amplifier and connect or feed part of it back to the input, we have what is called feedback. Feedback may either be negative feedback or positive feedback. Negative feedback is out of phase with the input signal, and positive feedback is in phase with the input signal. If the output signal that is fed back subtracts from the input signal, it is negative feedback and will result in the gain of the amplifier being reduced. Negative feedback is sometimes used to improve the frequency response of the amplifier or to reduce the amount of distortion in the amplifier. If the output signal that is fed back is in phase, that is, it adds to the input signal, it is positive feedback and will cause the amplifier to oscillate, and a whistle or squeal may result. This happens when the microphone of a public address system is brought too close to the front of the loudspeaker. Positive feedback is generally undesirable in an amplifier, and careful design is often necessary to prevent accidental positive feedback. All positive feedback is not bad, however. Positive feedback is necessary in oscillator circuits. In a properly designed oscillator circuit, it is not necessary to have an external input signal applied, but the circuit will begin to oscillate of its own accord when the output is connected to the input. Transistors are ideally suited for oscillators as they have a natural tendency to oscillate. Usually, we want the oscillator to provide a specific frequency. This can be accomplished by tuning the input or the output circuit. By tuning, we mean we balance out the circuit for a desired output. Resistors, inductors, and capacitors may be used to tune the oscillator to the desired frequency. Inductors are another name for coils. Tuned collector oscillators are quite common. Two of the most used are the Colpitts oscillator and the Hartley oscillator. This is a design of a Colpitts oscillator. The tuned circuit, which consists of the inductor, L, and the capacitors, C1 and C2, determines the frequency of oscillation. Capacitor CF provides the positive feedback from the output to the input. The inductor, in parallel with the tapped capacitors, is a characteristic of the Colpitts oscillator. The Hartley oscillator is similar to the Colpitts. However, note that the Hartley uses only one capacitor, C1, in the tuned circuit, and has a tapped inductor, L. Again, the positive feedback is provided by the capacitor, CF. The Colpitts and Hartley are only two examples of the many types of oscillators used in electronics and communications. Sometimes it is necessary to control the frequency of the oscillator very accurately. A quartz crystal may be used for this purpose. Crystals can be made to oscillate at very precise frequencies so that they can be used when several separate frequencies are close together, as would be the case with different channels in a CB radio. Each channel has a crystal-controlled oscillator on a particular frequency. The crystal keeps each channel at its proper place so it will not interfere with adjacent channels, and so that each radio set will broadcast and receive at the same frequency. It would not be possible to communicate with other CB operators if the frequency of each channel was not accurately controlled. If we have several channels, we can use a separate crystal to control the frequency of each channel, and this is often done. However, there is another method called frequency synthesis that is used also. In frequency synthesis, one crystal is used to accurately control the oscillator frequency, and all the other required frequencies are developed or synthesized from this single crystal frequency. Now let's look at some other types of electronic circuits, those used for modulation and demodulation. What do we mean by modulation? Modulation means modifying some characteristic of an AC wave or signal so that it varies in step with another AC wave or signal. The signal that is being modified is called the carrier, and the signal that is doing the modifying, or the changing of the carrier, is called the modulating signal. To modulate one wave or signal with another wave or signal, we must combine the two signals in an electronic circuit. We can recover the original modulating signal by demodulating, or as it is more commonly called, detecting. The two most common forms of modulation are amplitude modulation, or AM, and frequency modulation, or FM. Amplitude modulation, or AM, is used in ordinary AM radio broadcasting. Frequency modulation, or FM, is used in FM radio broadcasting. Both AM and FM are used in television broadcasting. Both AM and FM are used in some measuring systems and data handling systems. Let's look at amplitude modulation, or AM, first. We will have one signal, which we call the carrier, and another signal, which we call the modulating signal. The frequency of the carrier must be much, much higher than the frequency of the modulating signal. In AM radio broadcasting, the carrier is a radio frequency, or RF signal, generated by a crystal-controlled oscillator, and the modulating signal would be the announcer's voice, or the music. We apply both of these signals to the input of the modulating circuit, and the output will be a modulated signal, which looks like this. The frequency of the carrier remains the same, but the amplitude of the carrier now varies at the same rate as the input modulating signal. The electronic circuit which does the modulating can be an amplifier or an oscillator. When an amplifier is used as a modulator, the carrier is applied to the input of the amplifier, and the bias of the transistor is varied by the modulating signal. And the output of the amplifier is an amplitude modulated signal. As the carrier passes through the amplifier, the modulating signal will vary the bias of the transistor in the amplifier, and the varying of the bias will change the gain of the amplifier. When the gain of the amplifier is increased, the output is increased. And when the gain of the amplifier is decreased, the output will decrease. Thus, the amplitude of the carrier at the output of the amplifier will vary at the rate of the modulating signal. The carrier is applied to the input of the amplifier, but the modulating signal can be applied to either the base, the emitter, or the collector of the transistor in the amplifier. In a transformer-coupled amplifier, the carrier is applied to the amplifier right here. The modulating signal may be applied by a transformer to the base, like this, or to the emitter, like this, or to the collector, like this. When the modulating signal is applied to the base or emitter, it is called low-level modulation. And when the modulating signal is applied to the collector, it is called high-level modulation. Amplitude modulation can be obtained by using an oscillator instead of an amplifier. In this case, the carrier signal is generated by the oscillator, and the modulating signal varies the bias of the oscillator transistor. The amplitude of the carrier signal can be varied by varying the bias of the oscillator transistor. To review AM modulation using an oscillator, the oscillator generates the carrier, which is varied by the modulating frequency, and this results in the modulated wave output. The frequency of the carrier remains the same, but the amplitude of the carrier varies at the same rate as the modulating signal. When the modulated wave is received, it is necessary to recover the modulating signal from the modulated wave. We do this by demodulating or detecting. The modulated wave is applied to the AM detector, and the carrier is removed, leaving only the original modulating signal. The detector can be a diode circuit, like this. You will note this looks like the half-wave rectifier circuit that we saw in the program on rectifiers and power supplies. In fact, it is essentially the same circuit, and it operates the same way, except now we are operating at a much higher frequency. When the modulated signal is applied to the diode is forward biased and will conduct during the positive half of the modulated signal. The diode will be reverse biased and will not conduct during the negative half of the modulated signal. The output of the detector will be a rectified signal, which will vary at the rate of the modulating signal. The capacitor serves essentially the same purpose as it did in the power supply. In the detector, it removes the high-frequency ripple from the carrier. Now let's look at frequency modulation. In frequency modulation, or FM, the amplitude of the carrier remains constant, and the frequency of the carrier is varied by the modulating signal. In FM, the carrier is generated by an oscillator, and the frequency of the oscillator is varied by the modulating signal. Now let's repeat that. The carrier is generated by the oscillator, and when the modulating signal is applied, the frequency of the carrier will vary. When the modulated signal is received, it is demodulated in order to recover the modulating signal. The circuits used for FM modulation and demodulation are much more complicated than the ones used for AM, and will be covered at a later time in a more advanced portion of this course. Next time, we'll look at some special purpose semiconductors that we use in controlled circuits. I'm Dave Brown for Teletrain. I'm Dave Brown. Today, it's Chapter 7 in Teletrain series on the basics of solid-state electronics. Chapter 7 is entitled Special Purpose Semiconductors. There are many different special purpose semiconductors. We will cover some of the more common. They are the silicon-controlled rectifiers, the diac, the triac, and the field effect transistor. Let's examine the first of these, the silicon-controlled rectifier, which is commonly referred to as an SCR. However, before we get into this new material, let's briefly review some of the semiconductor devices we have covered previously. In earlier programs, we have covered the single p-in junction and saw that this could be used as a diode or rectifier. Then we progressed to the transistors, which had two p-in junctions. The transistor could either be a p-in-p transistor or an n-p-n transistor, depending on how the layers of p-type material and n-type material were arranged. Now we'll look at some semiconductor devices that have 4 layers, 2 layers of p-type material and 2 layers of n-type material. This 4-layer arrangement gives us 3 p-in junctions. There are numerous special semiconductor devices in this p-n family, but the most common one is the SCR. The SCR is used in control circuits to control the amount of current or voltage applied to a load. It is called a silicon-controlled rectifier because it is a rectifier which is controlled and is made from silicon material. As we just discussed, the 2-layer rectifier had 1 p-in junction and 2 leads. The SCR differs from the simple rectifier in that a 3rd lead is connected to one of the layers which will act to control the flow of current through the device. This 3rd lead is called the gate. The gate is connected to one of the layers of p-type material like this. The 3 leads are called the anode, the cathode, and the gate. This is the symbol for the SCR. It is a diode symbol with the line representing the gate added. The gate line may be shown slanting in from either side. You will recall that when we connected the plus terminal of a battery to the p-type material, which is the anode, and the negative terminal of the battery to the n-type material, which is the cathode, the p-in junction would be forward biased and would conduct. If we connect the plus terminal of the battery to the outermost layer of p-type material in the SCR and the negative terminal of the battery to the outermost layer of n-type material, the SCR will not conduct and no current will flow. In order for the SCR to conduct, it is not sufficient to have a positive or plus voltage on the anode and a negative or minus voltage on the cathode. A positive voltage must also be applied to the gate for current to flow through the SCR. When sufficient gate current flows, the SCR will turn on suddenly, much like a switch that is suddenly closed. In this respect, the SCR resembles a transistor. Remember, in a transistor, the base current controlled the amount of current flowing through the transistor. However, once the SCR is conducting, or in other words, current flows through it, the gate cannot control the amount of current which flows, nor can the gate turn off the SCR. Thus, the gate of an SCR is not equivalent to the base of a transistor. We can now see that the SCR is not like a rectifier or a transistor, but is an entirely different device used for different purposes. We now have the SCR turned on, or conducting. How can we turn it off, or stop it from conducting? Removing the positive gate voltage, or even applying a negative voltage to the gate terminal, will not turn it off. There are 2 ways we can turn off the device. One is to remove the voltage from the anode. The other is to place a short circuit from the anode to the cathode for a very short time. Either method will stop current from flowing through the SCR, and both methods are used. However, it is more common to turn the SCR off by removing the anode voltage. Let's look at the characteristic curve of the SCR to see what makes it different from an ordinary diode or rectifier. The curve of an ordinary diode looks like this. Remember that the diode did not conduct, or current did not flow, until the p-in junction became forward biased, and then the current increased like this. Now let's look at the characteristic curve of the SCR. It resembles the diode curve, except there is a portion of the curve that juts out. It is this characteristic that keeps the SCR turned off until gate voltage is applied. When the gate voltage is applied, then the SCR turns on and begins to conduct, and the curve will now look like this. After it is turned on, the SCR has characteristics similar to an ordinary diode, and removing the gate voltage will not affect the current flowing through the SCR. Now let's look at a circuit using the SCR as a control device. If we apply a positive voltage to terminal 1 and a negative voltage to terminal 2, the SCR will not conduct since the gate voltage is 0. Now let's close the switch. A positive voltage will be applied to the gate and the SCR will conduct. RL is the load. R1 is used to limit the gate current, and the diode is in the circuit to prevent gate current from flowing in the opposite direction if the polarity of the voltage on the input were reversed. If we apply an alternating current, or AC, to the input terminals 1 and 2, the SCR will act as a half-wave rectifier. It will conduct during the positive half cycle, but it will not conduct during the negative half cycle. Remember, we said that once the SCR was turned on, it would conduct until the anode voltage was removed. Well, when we apply an AC signal, the anode voltage is positive for 1/2 of the cycle, then it goes through 0 and becomes negative for 1/2 cycle. When the signal goes to 0, the anode voltage becomes 0 and thus is effectively removed. During the negative half cycle, the SCR is reverse biased and will not conduct. Thus, if we apply a 60 Hertz AC signal, the anode voltage will become 0 and be removed 60 times each second. The output of our SCR circuit will look like this. The SCR conducts during the positive half cycle. We will indicate it is conducting by shading the curve during the conducting part of the cycle. Let's modify the circuit by replacing the switch with a variable resistor R2. The amount of voltage applied to the gate can be regulated by the variable resistor R2, and this will determine when the gate will turn on the SCR. The variable resistor can be adjusted to let the SCR turn on anywhere in the positive half cycle between 0 and the maximum voltage. The output voltage across RL will look like this. The SCR will be conducting only during the shaded part of the cycle. If the load RL were replaced by an electric motor, the circuit could be used to control the speed of the motor by varying the time the voltage is applied to the motor. This is the principle used in variable speed electric drills. The trigger is connected to the variable resistor so that the position of the trigger determines the voltage applied to the motor. SCRs are used for motor controls for both small and large motors. Other uses include relay controls, time delay circuits, regulated power supplies, heater controls, phase controls, and other uses. The external appearance of the SCR is similar to a transistor. Since most applications require controlling large currents, most SCRs resemble power transistors, and adequate heat sink must be provided. Now let's turn our attention to the diac. The letters in the word diac may have originally stood for diodes and AC current, but if so, that distinction has been lost with usage. Today, diac and triac are pronounced as words, and the letters don't really stand for anything. The diac is a 5-layer device. It has 2 terminals and somewhat resembles 2 Zener diodes in parallel. The characteristic curve of the diac shows that it will conduct when either positive voltage or negative voltage of sufficient magnitude is applied. This is the symbol for the diac. Since the diac can conduct in either direction, it can be used in AC circuits and is often used in conjunction with the triac. Like the triac is a 5-layer device, but a gate is added to control the turn-on conditions. The triac is also somewhat like the SCR in this respect, but it differs from the SCR in that it can be turned on in both the positive and negative half cycles. The characteristic curve of the triac looks like this, and as you can see, this portion resembles the SCR curve here and an inverted SCR curve here. This is the symbol for the triac. Let's look at a control circuit using a diac and a triac. This circuit controls the voltage applied to the load RL by switching the triac on and off during both the positive and negative half cycle. The shaded portion of the cycle indicates conduction. The amount of time the triac is conducting is controlled by R1. The capacitor, C, allows the AC to flow, but prevents the rectified DC from flowing. We can replace the load resistor, RL, with a light bulb and have a light control circuit, or as it is more often called, a dimmer circuit. The position of the variable resistor will determine how much voltage is applied to the bulb, and hence how bright it is. We have seen how semiconductor devices can be used to control circuits. In many applications, a resistor could be used to control the voltage applied to a motor or light bulb, but all the current flowing through the motor or bulb would have to flow through the resistor all the time. Since power is determined by the current squared times the resistance, a lot of power would be wasted as heat in the resistor. In the SCR and triac circuits, current flows only during part of the cycle. Therefore, the current is turned off during the rest of the cycle, and power is not wasted. The final semiconductor device we will look at today is the field effect transistor, or FET. The field effect transistor differs from the regular transistor, or junction transistor, in that it is a voltage control device rather than a current control device. It may consist of a bar of N-type material with P-type material embedded in a band around it. This is called an N-channel device, and this is the symbol for an N-channel FET. It may consist of a bar of P-type material with N-type material embedded around it, in which case it is called a P-channel device. And this is the symbol for a P-channel FET. The 3 terminals are called the source, gate, and drain. These correspond to the emitter, base, and collector of a regular junction transistor. The amount of current flowing from the drain to the source is controlled by a voltage applied to the gate. Since the field effect transistor is a voltage control device, no gate current will flow. This is in contrast to a junction transistor where base current always flows when it is conducting. This is a typical small signal amplifier circuit using an in-channel field effect transistor. Amplifiers using field effect transistors have extremely high input resistance, often several million ohms. Because of this high input resistance, they are often used in electronic meters and instruments. Field effect transistors are also low noise devices, which makes them useful in stereo and hi-fi applications and in medical electronic circuits. This concludes Chapter 7. It is also the conclusion of teletrain's basic course on solid-state electronics. In this 7-chapter course, we have endeavored to give you a background upon which to build an understanding of solid-state electronics. I'm Dave Brown for teletrain.